Hello, everyone. All right. Excuse me. This lesson will probably be a little bit faster because it's something we've done before. We did it first semester. It was kind of one of those last lessons, but now we're combining it with the derivative graph or the derivative equation as opposed to the original. So the goal today is to be able to find absolute extrema. What is an absolute extreme? Well, quick refresher. If I have a function that looks like this, let's say it goes like here, 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 maybe something like this, in this interval from, let's say right here to over here. So if I give you an interval enclosed between the green, the absolute max means that highest point the graph hits and the absolute min is the lowest point. There are two places this can occur. They can occur, so absolute extrema occur at endpoints, or they can occur at critical points. So in this case, right here, this is the endpoint. That looks to be the lowest point. So I would call this the absolute min. And notice this interval is here. We have a critical point here. There's a relative min, but it's not the absolute. Here's a relative max, but it's not the absolute max. Right there, that's the absolute max. It's the highest point. So we did this first semester. There's a video all about it where we have to find the absolute extrema. And if I give you the function, it's not that hard. If I give you the function, you take the derivative, set it equal to 0, find the critical points, and then find all the values. Today, we're not going to have to find the derivative because we're going to have the derivative, but we're going to have to list what we call the candidates, and then, find the value for each candidate. So I got two examples for you because this kind of combines math we've already been doing. Example, given, I'm going to give you the derivative function, f prime of x equals, I'll give you a really simple one. Let's do x minus 3 times x minus 1. Find the absolute extrema, or absolute max or min, over, and I got to give you an interval. I have to, otherwise it can keep going up and up and up and up, which this one does. Well, in one direction. Because it's a squared, so the original function is a cubic, which means it keeps going up. So I have to give you an interval. So let's go over the interval from -1 to 5. Another thing I have to give you is an initial condition. So with f of, let's do f of 1. Nope. F of 0. Fine. F of 0 equals 2. All right, so this is a pretty typical problem. And we can go through it. So here's the way it works. The first thing I always want you to do when you see absolute extrema, that should immediately tell you to list the candidates. Candidates means the potential places where you could have an absolute maximum or an absolute minimum. And there are two types, like I said above, endpoints and critical points. So two of them you get for free. You get f of -1. You don't get, you don't get the value. You're gonna have to find it, but you know it's this endpoint. And f of 5, we're gonna have to find that one. Then you got to find the other ones, which are critical points. So those were your endpoints. These two. These were our endpoints, which will be given by the interval. But now we need the critical points. So to find the critical points, we got to set the derivative equal to 0. You can graph it and do it that way, or I gave you a really nice factored one. So we can either graph it, find the roots of the derivative, or we can see that there are two of them here. It's going to be 3. It's going to be 1. So essentially, the four candidates are x equals -1, x equals 5, x equals 3, x equals 1. So in other words, the candidates are x equals -1, 1, 3, and 5. The absolute max and absolute min have to occur at one of these spots. So how do we find them? We have to do accumulation. Initial condition plus accumulation. So let's start with f of 1. We'll do the backwards one in a second, just a reminder of how that works. F of 1 will be f of 0 plus the accumulation from 0 to 1 of our derivative. F of 3 will be f of 0 plus our accumulation from 0 to 3 of our derivative. This is actually really straightforward. We don't have to worry if the function changes direction or anything, because accumulation accounts for positive area and negative area. F of 5 is f of 0 plus the accumulation from 0 to 5, f prime of x dx. And then this one's the one you have to be careful, f of 0 plus the accumulation from 0 to negative 1, which, since we're going to use Desmos doesn't care that the bounds are out of order. If we used a graph, we'd have to flip it. So just a reminder that, if we flip the bounds and were to do this from left to right, we would have to, flip the bounds and make it a minus. But Desmos can handle that calculation alone. Okay, so we need to find all of these values. By the way, as we continue to do more and more accumulation, never forget the fundamental theorem of calculus is always kind of present in these. If I take the derivative of the antiderivative, as we saw in last lesson, kind of, we actually did it in the reverse order, but this is the fundamental theorem of calculus. If I take the antiderivative of the derivative, so like right here, and then plug in top minus bottom, this really is the same as f of 0 plus antiderivative of the derivative, and then plug in 5 minus plug in 0. And then these two cancel, which leaves me with this. That's why this calculation works the way it does. But again, we don't really need to think about that when we're dealing with Desmos. We let Desmos find the antiderivative and evaluate it for us. So let's find all of these values, and then I'll make sure you can state your answer correctly. Okay, so we have our function. I will bring it down here just to make sure that you understand exactly what I'm typing into Desmos. And yes, we're going to begin using the graphing calculators soon. Okay. Not quite, but soon. So we have our derivative. I'll just call it d of x, or you can call it f of x on your videos. Some of you guys did one, some of you did the other. I'll just call it d. So I keep it straight. So there's the derivative graph, roots at 1 and 0 to 3, like we said. So to get f of negative 1, it was f of 0, and f of 0 was 2, plus the accumulation from 0 to negative 1, d of x dx. So again, that might be a little weird. Maybe we should just go back to f. And we have that value, negative 3.33. So this first one, negative 3.33. We have found that value in the original. And then we just continue along. So once you've done one, it's basically the same thing over and over and over. So I almost can just copy this and do from 0 to 1 now. That's positive 3.33 repeating. I guess I should keep 3 decimal places, like I keep telling you. To get 3, f of 0, which was 2, plus the accumulation from 0 to 3, which is 2. And then the last one, oops, I put these in the wrong spot. This was 3.33, sorry. F of 5 is this last one. F of 5. 8.667. Oops. And these are actual values in the original. So the original function has this value, negative 1, negative 3.333. This one is 5, 8.667. This one was 3, 2, and this one was 1, 3.333. So really, if you think about it, if you go back to the original function, or sorry, the derivative graph, does these values make sense? So originally we started at -1, -3, and then the graph went up for a while. Yeah, that makes sense. 1 should be higher than -1. And then from -1 to 3, we went down. So it makes sense that this is lower. And then from 3 on, we went up. So it makes sense that this is higher. So finally, you just get to do an analysis and see which one's the highest, which one's the lowest. So it looks like this one right here. Sorry, this one right here. There's your absolute min. It happened at the endpoint. And where's the absolute max? I gave a boring problem. The absolute max happened at the endpoint also. That's okay. Absolute min happened at an endpoint. Absolute max happened at an endpoint. Didn't happen at the critical points this time. Okay, but this is one more piece to all of the accumulation type stuff we have to be able to do. Always using a derivative to talk about the original function. And this calculation is pretty important because a lot of times we'll want to know when was the most, or for example, when was the particle farthest forward? That would be an absolute max type problem. Or if we're doing an accumulation and we have the rate at which people are entering an auditorium, I can find the time when the maximum number of people were in the auditorium. So this is a really important calculation for finding when the maximum of something occurs. But it always falls back to initial condition plus accumulation. Okay, one more thing before we do the last example. In your homework, I do this. Sometimes you'll see the problem this way. Other times you'll say, given g of x equals 2 to x. Well, it's not going to work exactly the same in this one. I guess it'd be more wherever the 0. The point is, if I give you this setup, let's just say it was 1 or something. F of t dt. And then I said f of t equals x minus 3 times x minus 1. Sorry, with t's though. This is the same exact setup. I'm giving you an accumulation function, and in the discussion, I ask you to take the derivative of this. The derivative of this, left side, derivative and antiderivative cancel, and you plug in the top bound. So in other words, it's like me saying, I've given you the derivative equation, and now do things about the original. Okay, so don't be scared when I start combining these topics together. Problems 1 and 2 on the homework are exactly this exact same problem, just written kind of 2 different ways. One's using, hey, I'm giving you the derivative. The other one's saying, hey, I'm giving you an accumulation function, which works the same way. All right, let's do one more, but this time let's do it from a graphical approach. So in this case, get out of here. Where did it go? So this time, let's say I do it this way. Ready? Let's say given, and so I'm going to do it the accumulation side of things. Given g of x is equal to the accumulation from 0 to, let's say, x, obviously, f of t dt, where the graph of f is given, find the absolute max min of g. All right, so what is really going on here? If this is the graph of f, you're going to keep seeing me say this to you. When you see an accumulation function like this, that just means if I take the derivative of both sides, from last lesson, the derivative and integral cancel, and you can plug in the top bound. In other words, they're giving you the derivative graph. So just think about it like the last problem. This is the derivative graph, and we're asking questions about the original function. But in this case, we just defined it differently. But at the end of the day, that's really what we're doing. All right, so everything goes the same. And I haven't given the interval. Let's just say the interval is included by the graph, so from -2 to 10. So if I give you a graph and the graph cuts off, typically it's the bounds by the end of the graph. So nothing changes. We start by listing candidates. Well, you have your two, I want to make sure we can see all this. Okay. You have your two endpoints, so we're going to have to find g of -2, and we're going to have to find g of 10. Now we also have our critical points. Well, that's where the derivative graph, which is this, equals 0. So we have one right here, we have one right here. So g of 0 we're going to have to find, but that's going to be important in a second. And we're going to have to find g of 9. All right. So I'm going to cover that a little bit because I think you know what the question I'm asking is. All right, let's begin. So first, when I give you an accumulation function like this, you don't have to worry about initial condition. It's built in by the bottom bound. I kind of mentioned that last video. So literally, you plug -2 into the bound for the accumulation function. And what is this asking? It's asking for the area under the curve, but the bounds are flipped. So put a negative, flip the bounds. And all it wants you to do is find the area from -2 to 0 and make it negative. So we have this area right here. We are accumulating from -2 to 0. That is a triangle. 2 times 4 is 8. Half of 8 is 4. So it's +4, but remember I flipped the bounds, so it's negative. So that value is -4. So the thing to remember when I give you the accumulation function is that bottom bound has to do with the initial condition. You're going to see right here when I find g of 0. When I find g of 0, that means plug 0 into the value for x. And this says, what is the accumulation from 0 to 0? Well, you can't, if the top bound is the same as the bottom, that's just 0. So it's like I gave you the initial condition was g of 0 equals 0. That bottom bound sets the initial condition when you're given an accumulation function. All right, let's find g of 9. G of 9, same thing. We don't have to worry about initial condition. It's kind of built in. 0 to 9, f of t, dt, which looks like if I want to find the area from 0 to 9, is all of this. The bounds are in the correct order. It's a triangle. The height of the triangle is 6. It's 1/2. 6 times the base, which is 9. 6 times 9, 54. Half of that is 27, but it's below the x-axis, so I'll make it negative. That is actually negative area. And then the last one, to find g of 10, I ran out of room a little bit, but 0 to 10, area under the curve. From 0 to 10, well, we already found this, -27. We just need to add this little guy, which is, looks like a half. So -27 plus 1/2, which is -26.5. And that's it. So now we have all the work. We just need to talk about which one's the max. Well, this is interesting. Our max occurred right here. So g of 0 equals 0 was our max. So I would say it this way. The absolute max occurred at x equals 0 with a value of 0, or you can just say g of 0 equals 0 is the max. And the min occurred right here, this one. So g of 9 equal -27 is the absolute min. So in this case, both of our maxes and mins occurred at critical points. Does that make sense? So this is where you can start to combine your idea of curve sketching with intuitively, how do you know what's going on? Well, think about curve sketching. We know that this area right here, if I started from -2, means the original function went up. At 0, it flipped from a positive to a negative, which means it's a max. Then we went down for an incredibly long time. All of this was how much we went down. We had an inflection point right here, which means we like started decreasing or decreasing at a decreasing rate. And then right here is where we began increasing again. We have another critical point. So kind of like this, and then we went up for a tiny bit. So if you can put those together, it makes sense that this would be the max in the original, and this would be the min in the original at 9 and at 0. But you can't just say that. So on the FRQs, they're going to ask you to find the absolute max, absolute min. You can't just say, well, the graph accumulation up was a lot less than the accumulation down. Like, the best way is to do the whole candidates approach, state the candidates, find the values, and then you're just letting the math do the talking. That's the idea. All right, so this is one of our, we're getting to the point where we have enough accumulation topics that mostly we've seen all of the kind of the basic stuff I could ask you in an accumulation FRQ. The next lesson is going to bring one more thing into all of this, and it's probably the longest one. So we'll see where we're at after that. But at the end of the day, this one is accumulation function, or I give you the derivative and you have to accumulate, and it's just finding values like we've been doing. But now you're using that whole candidates idea from before. All right, that's it.